Yeah, we'll add 12. I can add 12 to the list. All right, so next up, we've got question 7. So that was question 4, question 7. Oh yeah, we did question 7 in office hours today. All right, we're gonna need the other slide. I'm gonna need more information than that. Ka is 1.8 times 10 to the minus 4. All right, so formic acid, I'll tell you right now. Correct, Jack, yeah. Right, we're looking for what's 1-to-1 relative to what we put in. And that's gonna tell you, like I was saying in the previous case, right? In the previous case, because for every 1 silver carbonate that went into solution, we get 1 carbonate. So that's telling us the molar solubility of silver carbonate. Because if I had 2 molar carbonate in solution, that would tell me 2 molar silver carbonate had to go into solution. So yeah, we're looking for the one that's a 1-to-1 ratio. So if Jack and I were to compete in an athletic contest, would people attend that event to watch me hopefully destroy Jack in an athletic event? Now Jack's gonna kick my butt, yeah. So for the exam on tomorrow, we're definitely gonna have a question like this, like question 7, right? We've got a weak acid, formic acid, ionizes to give us, right, our hydronium, the conjugate base. They tell us the Ka, and they tell us our concentration of our weak acid, right? Our concentration is 0.15. So if we want to set up the ice table, right, initially we're going to have 0.15, 0, and 0. We start with 0.15 acid, they tell us that, 0 hydronium, 0 conjugate base. As this goes into solution, some of the formic acid is going to ionize. It's going to form some hydronium and some conjugate base. Those concentrations are equal. We can call them both X. And at equilibrium, we're going to have X amount of hydronium and X amount of the conjugate base. However, this is where we made a slight change, right? We said we could ignore this change in X if we know an initial concentration, right? Because our change in X for these weak acids or weak bases, X is negligible. We can ignore that and basically say at equilibrium, I'm going to have 0.5 molar of my acid. Because negligible amount of concentration lost. Another question that came up in office hours today, why do we subtract here? Why are we adding here? We subtract from the reactant side because this is going into solution. We add on the product side because this is being made. So that concentration is going up on the product side. All right, so now we can set up our Ka. Ka, it helps if I don't use the lightsaber, right? Ka equals my hydronium times the concentration of the conjugate base all over the concentration of my acid. So we know Ka is 1.8 times 10 to the minus 4. Hydronium was X, our conjugate base was X, and 0.15 was our concentration of Ha. I'm going to multiply both sides by 0.15. All right, so that cancels out. I get X squared equals 10 to the minus 4 times 0.15. Get 2.7 times 10 to the minus 5. Take the square root of that to get X, right? So the square root is 5.2 times 10 to the minus 3. What is X, right? X is our hydronium concentration. So the last step is to find pH, right? pH is the negative log of my hydronium concentration. All right, so pH is the negative log of 5.2 times 10 to the minus 3. pH equals negative log 2.28 for my pH. Right, so formic acid, this is at equilibrium, Rochelle. There is a reaction, and that's why there's an equilibrium, right? It's going back and forth. So we've got some formic acid, some of it ionizes, forms the conjugate base, some of that conjugate base reacts in the reverse direction. So we have that equilibrium because it's reacting in both directions. Yeah. Because once we get to equilibrium, right, the reaction's still occurring, but it's occurring equal rates, opposite direction. So we have to establish that equilibrium. So to establish that equilibrium, we have to make some of the products, and then we get that balance. And then at equilibrium, it's still reacting, but the concentration's not changed. Right, so some of it goes forward. We keep pushing material forward, but some of it's coming back. And at equilibrium, the same rate that it's going forward, it's coming back. But we've made some product before it reached equilibrium. We had to make some product, so that's why it'll always be, you know, positive on our product side. For blank 8 and 9, we put it in scientific notation instead of. I'm gonna have to check blank 8 and 9. Let's see, my top hat tab. Oh, okay. So Kareen said 0.0052. Yeah, I think in the table there's not an ability to put it in scientific notation. So I think you might be okay in just putting it in the numbers like Kareen said. Question 8. Oh, okay. Question 8's the same thing, just with a base. So again, like the previous question, you're definitely gonna have a question like this, you know, on the exam. Similarly, okay, let me just take a quick look then. Blanks 5 and 6. So for question 7, yeah, they're just looking for like plus X for blank 5 and 6, right? Yeah, because that's what we were doing. Yeah, we were adding in, right? We needed it in terms of what we're changing. So yeah, plus X for 5 and 6. So this is, right, same thing except for with a base. So we start off with a concentration, right? I've got 0.75. And thank you, Callie, for helping David with that. Some of it goes into equilibrium. Again, we can ignore that and say, okay, at equilibrium, I'm going to have 0.75. I've got 0 of the conjugate acid, 0 of the hydroxide. We're going to gain X amount of both. And at equilibrium, right, I'm going to have X conjugate acid, X hydroxide concentration. The only trick with these, right, is we have one more step basically, because Kb equals the concentration of my conjugate acid times hydroxide all over the concentration of my base. We know Kb, 6.5 times 10 to the minus 5, right? X times X all over my initial concentration, 0.75. Multiply both sides by 0.75, we're going to get X squared. So 6.5 times 10 to the minus 5 times 0.75, 4.875 times 10 to the minus 5, square root of both sides is going to give us X. So I get x equals 6.98 times 10 to the minus 3. The only difference here is that x is hydroxide. So we're actually going to start with finding POH first and then finding the pH. So we know POH equals the negative log of my hydroxide concentration, right? So POH equals, and then we know pH plus POH equals 14. So pH equals, so first things first, right? Negative log of that concentration. I get a POH of 2.156. And that makes my pH, like 11.84 for my pH of that. So that's the trick. When you're working with KB, when you're working with bases, we usually find hydroxide first, but the problems usually ask for pH. So you have to go hydroxide, POH, then pH. And as someone pointed out in office hours today, if you make that mistake, the wrong answer will be there. So POH will be there as an answer. All right, any questions on 7 or 8? Let's see if I can. So we'll do 9 and 10 together. Yeah, even though we did 10 in class. I guess we did 11 in class. So 9, 10, and 11. So question 9, what can we use to make a buffer? Weak acid, conjugate base. It's going to be the #1 way to make a buffer. So if we look, choice A, I have strong acid, strong base. Nope, won't make a buffer. I have boron trifluoride and ammonia. Ammonia is a weak base, boron trifluoride, not an acid, not a base. Yeah, what did I say, Karine? Yeah, oh yeah, a weak base and its conjugate acid. That pair would work as well, correct. Nitric acid, strong acid. So no. Yeah, we have the conjugate base, but we have a strong acid. Sodium hydroxide, ammonium hydroxide, a strong base, another base. No, that's not a buffer. So HF, weak acid, potassium fluoride, that gives us the conjugate base. So that would make a buffer. Sodium nitrate would dissociate. And this is what we kind of talked about a bit in office hours today, that I don't know if it came up a lot in class, but when we're thinking about basicity and these conjugate bases, right? So something like HF will react with water to form hydronium and fluoride because it's a weak acid, whereas something like nitric acid, HNO3, is a strong acid. So when that reacts and forms hydronium and nitrate. So I don't know if this came up too much, but the reason why we want to differentiate these, HF is a weak acid, and that means we're at equilibrium. Because we're at equilibrium, the forward reaction occurs, HF behaves like an acid, but the reverse reaction also occurs. Fluoride behaves like a base. So it reacts with hydronium, reforms hydrogen fluoride. So the conjugate base of a weak acid behaves like a base. It's a weak base. So if I added fluoride to solution, it would change the pH of that solution. This is where the nitrate differentiates it, right? Nitric acid, any strong acid, ionizes completely. So nitrate, it's the conjugate base of a strong acid, but because it's the conjugate base of a strong acid, it's not going to behave like a base. There is no equilibrium here, which means there is no reverse reaction. So I can add sodium nitrate to solution. It's not going to change the pH. I could add sodium chloride. I could add sodium bromide. I could add sodium iodide, sodium chlorate. All of those salts are not going to change the pH of the solution because these conjugate bases are all conjugate bases of strong acids. And so, yeah, to answer Callie's question and Maddie's question, right? When we started this acid-base unit, I said, know a handful of the strong acids. And so it should be easy to get a few of them because 3 of them are halogen-based acids. So HCl, HBr, HI, nitric acid is 1. The first proton and sulfuric acid is 1. And HClO3, HClO4 are the other 2. So 7 strong acids. I said, if you know a good 5 of those are the strong acids. These conjugate bases won't behave like bases. Any other acid we're going to see is going to be a weak acid. And so, yeah, Maddie and Callie, that just helps because if we know the strong acids, anything else is a weak acid. And to answer Rochelle's question, these are all strong acids. To answer Rochelle's question, I mean, water, when it reacts with itself, it's going to make its own conjugate acid and conjugate base. But no, when we're looking for a weak acid and its conjugate base or a weak base and its conjugate acid, water is not going to be that pair, right? Water is going to be the hydronium. Water is going to be in the hydroxide, but it's not the pair with our weak acid or with our weak base. Right, and then question 10. Question 10 here. No, I mean E. Oh, sorry. I thought you were looking at this list here. Yeah, sodium hydroxide is a strong base, and ammonium hydroxide is going to give us hydroxide. So, no, we have a strong base. This isn't going to work to give us a buffer. Yeah, we'll get to question 16, I guess, later. Question 10, right? Classic buffer question. You'll have a buffer question on the exam tomorrow. I've got a weak acid, its conjugate base, an equal concentration. To that, I add a strong acid. The acid, just think of it, if you adding an acid to a buffer, you're going to add it to the acid that's in solution. The concentration gets added there, and it does that by reacting with the conjugate base. There we go, 3rd time. So I'm going to subtract from that conjugate base concentration. Both concentrations need to change, right? My acid concentration goes from 1 to 1.1, and the base, conjugate base, goes from 1 to 0.9. Now I can use the Henderson-Hasselbalch equation, right? pH equals pKa, which is the negative log of my Ka plus the concentration of my base over my acid. Plug those in, and we get a pH for number 10 of around 4.8. Number 11, we did this one in one of the classes. The only difference here for number 11 is we're adding a strong base this time. So I'm adding base, I'm going to add that concentration to the conjugate base, right? I'm adding more base to the solution. So I add that concentration here, and it does that by reacting with the weak acid. So I subtract that concentration there. Again, both of these concentrations have to change in a buffer question. Back to the Henderson-Hasselbalch, plug in, right? Negative log of Ka plus the log of my base over my acid. And this time I get a pH of like 4.65 for question 11.